Welcome to this video on the application of exponential functions. By the end of this video, you should be able to model exponential functions in real-world scenarios and come up with answers for a specified amount of time. All right, so there's a couple pieces of important vocabulary you need to know as part of this that are going to show up a lot. The first word is interest. Interest is money that's been paid to an account holder by a bank for the bank being able to use the account holder's money. So when you put money in the bank, it just doesn't sit in the bank. The bank uses it and invests it and does different things so the bank can make more money. And so they pay you a little bit of money to allow them to do that. There's two kinds of interest that we're going to talk about. We're going to talk about simple interest, which is paid one time per year. And we're going to talk about compound interest that's paid multiple times per year. Two other words that show up an awful lot that you need to know that you might not already know is the words appreciation and depreciation. When we're talking about money or objects that have a value, appreciation means it's gaining value after purchase, and this is going to be a growth situation because it's worth more. So it's going to start at some lower amount and go up and be worth more. So that's a growth. Depreciation is when an object loses value after purchase. That's a decay because it starts with some value, but then it begins to lose value over time. Okay, so there's some formulas that you will need to be using. We have our growth formula, and it's growing because we're adding in between. We have a decay formula, and we can tell it's decay because it's subtracting. And then we have our compound formula for a compound interest, and you can see it's just like the growth formula. The only difference is your R here is going to be divided by N, and then N is going to be multiplying in your exponent too. So your compounding is going to get used more than once. So we'll go over that. On our formula sheet, the only one that they put on here is the compound interest formula. So if they're talking growth, you would just put plus. If they were talking about something decaying, you would do a minus here. But overall, you've got pretty much the formula that you need because they all work together. All right, so let's take a look at these formulas and what do all of these letters mean. So in our A value here, the A value is the final amount. How much do you have at the end? So that's your final amount. The P is something called principal. So when you make any sort of investment or deposit, the principal is the beginning amount. How much are you starting with? So you'll be putting that amount in this spot. So beginning amount. The R is going to be, it's a rate of some kind. It's going to be expressed as a percentage. So you're going to divide the percent by 100 to remove the percent sign, and then that's the number that you're going to plug into this formula. And then T stands for time. How much time are we talking about here? Okay, so that works on growth and decay. Our compound has all of these same letters, but it has a new letter with N. N is the number of compounds per year. How many times are they going to pay interest per year is really what it's saying. But it's how many times in the year, so that's going to be a specific number that we'll have to plug in. Okay, so when we're reading our problems, words we want to look for, if we're looking for a growth problem, you'll see words like appreciate, because that means going up, increase, gains value, doubles. A doubling means your B value is 2. 2 times also means your B value is 2. You could see 3 times, which would be your B value equals 3. When we're thinking about exponential growth. So sometimes this number, the 1 plus R or the 1 minus R, that's actually your B value as it relates back to our original equation. Remember when we had y equals A times B to the X. Okay, so if they use the words doubles 2 times, 3 times, they're actually doing the math for you, and you just stick the number in there. You don't have to do any addition or subtraction to it. In our decay, you'll look for words like depreciate, decrease, loses values, halves, that means the B value is 1/2. Really, you're saying what's in the parentheses is, so the 1 minus R would be 1/2. Quarters, that 1 minus R would be 1/4. Okay, so they've already done the 1 minus R and they're telling you the result, and you just plug that number in. Now, for compounding, it's compounding however many times yearly, and so they're going to say some of these words. These are the most common ways that interest is paid. If the interest is paid yearly or annually, well, there's only 1 year in a year. So really, if it's saying yearly, you're going to want to come back over here and use just the plain old growth. You don't need to divide, because you would be dividing by 1 here and then multiplying by 1 there. So it's not changing the value at all. You can use either equation, but it's easier to just use that one. Quarterly, there are 4 quarters in a year, so your end value would be 4. Monthly, remember we're talking about a year, so there are 12 months in a year, so you would be paid interest 12 times. We have weekly, there are 52 weeks in a year, so they would pay you interest 52 times in the year. And then we have daily. In the banking world, they use 365 days, even though it's like 365 and a quarter days. But they just go with the round number of 365 for your how many times they're going to pay interest. They pay you interest every single day. So those are our different compounding. So let's try a couple of these and kind of get used to pulling the information out and plugging it into the formula. All right, so in 2000, the cost of a tuition at a state university was $4,300. Okay, that's how much we're starting out. So that's that principal amount right there. That's the beginning amount. During the next 8 years, the tuition rose, that means goes up 4%. 4% is your R value each year. So I want you to take so we're going to take 4%, 4 and divide it by 100. And that's how we're going to plug it into the equation, is 0.04. Okay. So we're going to write a model. A model is just an equation for tuition Y after T years. So what they're saying is, instead of the A, we're going to write Y equals. Now we had our principal amount when we look at our equation. And our principal amount was how much it was in the first time they were talking about it, $4,300. Then we had the parenthesis. We're rising, so this is a growth. So we're going to say 1 plus R. So 1 plus, and R is 0.04. Close it, and instead of the T, we're just going to write the T. This is the model for any amount of time, okay? So when they say model, they want you to write an equation that you could use to find out any time possible. Now, the question asks, how much would it cost to attend college in 2010? Well, they started in the year 2000, so 2010 will give you a T value of 10 years. So you're going to plug in 10 there. So let's set that up. So we have Y equals 4,300. I'm going to go ahead and add this together. 1 plus 0.04 is 1.04. And we're talking about 10 years. So let's take our calculator, and we're going to say 4,300 parenthesis 1.04, close it, and we're going to write it just like this, rise up and put a 10 in the exponent. And I get this number. Now we're talking about money, so we want to go 2 decimal places out because money has 2 decimal places. So I'm going to put my $sign. So in 2010, if it's following the same model, the tuition would be $6,365.05. Okay, So we want to do the same thing for 20 years. 2020 is 20 years after what they were talking about. So let's write this out. 4,300 times 1.04. And now our t here is 20. So we want to plug 20 in. Okay, so I'm just going to go copy what I had and change the 10 to a 20 and press enter. This would be the tuition in 2020 if it keeps following the same model. So we have our dollar sign because we're still talking about money, $9,421. And it says 82 cents and the next number is a 9. So I'm going to go ahead and call that 83 cents. So it got to be a whole lot more expensive, more than double in 20 years. Okay, so there's real life applications. You can figure out numbers, what things are worth, that kind of stuff using our exponential growth and decay applications. All right, let's try some more. So we're going to flip this over. So in this scenario, we have a Kia Optima. It's a 2015 Kia Optima, and it depreciates. Depreciates means decays. That means we're going to use that 1 minus R in our equation. Okay? So it's going to depreciate or lose value at a rate of 12.6% per year. So R equals, if I divide 12.6 divided by 100, I get 0.126. Okay, so that's going to be the number we're going to plug into our equation. The car was bought for $32,000. So that's the amount you begin with. That's your principal amount. Okay, so we're going to take, remember we have our final amount is our principal 1 minus R raised to the t. So we're going to write the model. So the t is going to stay put because we want it to be for any amount of time. Okay, what amount will we have? We had a principal amount of $32,000. And then our parenthesis, and we're going to do 1 minus, because this is a decay problem because it's losing value, 0.126 raised to the t. For any period of time, we can figure it out following this model. Okay, so now how much was the car worth in 2018? Well, if it's bought in 2015, and now they're asking about 2018, that gives you a t value of 3 years. Okay, so let's plug this in. So our final amount, we're going to say 32,000. I'm going to go ahead and find out 1 minus 0.126 is 0.874. I went ahead and did the subtraction because a lot of times you're not going to see it written like this. You're going to just see the actual math done with it. And my t here is 3. So let's take our handy dandy calculator. We have 32,000, parenthesis 0.874, and raise it up to a 3. And the car, after 3 years of owning it, the car is now worth $21,364.08. So it lost a lot of value in 3 years. It lost more than $10,000 of value in those 3 years. Okay, so that's the depreciation. It's losing value. Well, what is the car worth now? Well, it's 2021 now, as of this video. So 2021 is 6 years from 2015. So our time there will be 6. So we're going to use the same setup. We'll say 32,000 times 0.874. And now our time is going to be 6. So I'm going to go and just copy and paste what I already have in there so I can just change the exponent to 6. Now the car is only worth $14,263.25. So it's lost quite a bit of value in the 6 years that it had been owned. Okay, so and that's what happens to cars, is they lose value. As soon as you buy it, it's worth less. As soon as you drive off the lot where you bought it, it's worth less. They lose values. Houses, on the other hand, tend to gain value. So it's just about where you put your money and whether it will be worth more or less after you invest in something. So now let's take a look at compounding. So compounding, I want to remind you the formula. It was real similar. It had the 1 plus, but the R was going to be divided by your number of compounds. And then you can take your number of compounds times the time. Okay, so we have a little bit of extra stuff that we need to put in here. So we're going to invest $1,000. You got $1,000 for graduating from something. I don't know what you graduated from. So that's your beginning amount. That's your principal. We're going to start with $1,000. The bank is offering 4% interest. So that's your R value. If you take 4 and divide it by 100, you get 0.04. And so we're going to calculate how much money we'll have after 10 years. So we're going to say time is 10 years if the bank compounds, and we have some different compounding scenarios here. So let's look at quarterly. Remember, quarterly, your N is 4 because there's 4 quarters in a year. So if we set this up, we would start with $1,000 in our principal. And then we'll say 1 plus 0.04 is our R, but the R is divided by the number of compounds, which is 4. So we're going to say divide by 4. And then our exponent is the number of compounds, which is 4, times our time, which we already said was 10 years. Okay, I don't want to put this in the calculator yet. Let's set these all up and kind of look at them. They're very, very similar. Monthly, there are 12 months in a year. So our N is going to be 12. We're going to be paid interest 12 times. So everything looks the same, except right there, instead of dividing by 4, we're now going to divide by 12. And we're going to say 12 times 10 there. Okay, how about weekly? Weekly, remember there are 52 weeks in a year. So we'll set this up. We got $1,000 to start with, 1 plus 0.04, but our compounding is now, they're going to pay us 52 times, so we're going to divide by 52, and then 52 times the 10 years. What's that going to be? And then finally our daily. Daily has an N of 365, so we'll set this up. Okay, 365 goes in the N spot, and the N occurs right there again, times 10. All right, so do you think you're going to get more money the more times you're paid interest? Well, it sure seems that way for sure. Are you going to get a lot more money? So let's say we were shopping between 4 banks, and these are the different things that they're offering for us. So let's take a look. So I'm going to take my calculator. I'm going to put in the $1,000, parenthesis, 1 plus, let's do another parenthesis here, 0.04 divided by 4 and close it. So that is just for this fraction. What we really did is we put this fraction in a parenthesis. So now we need to do another parenthesis to close that out. And we're going to raise it up to 4 times 10. Now, if you use the parentheses like this, I'm going to show you, you can just keep cutting and pasting and save yourself a little bit of work here. That might make it a little bit easier. So if we leave the money in the bank, we put $1,000 in and we never put any more money in, and we came back 10 years later, we would now have $1,488.86. So I'm getting paid some interest here. $489 worth of interest. Okay, and I didn't do anything. I just left it in the bank for 10 years. So that's if they pay me interest 4 times a year. What if they pay me interest every single month? Okay, so just go up, highlight that and hit enter, and it'll just paste it down where we are, because we're going to have to change, because instead of 4 we now have a 12 here. So we're going to have to do a little extra typing because our numbers are a little bit longer. So 12 and then 12 times 10. So make sure it looks like our equation. We divided by 12 and we multiplied by 12. So let's see how much money if we put it in this other bank that's going to pay us interest monthly. Huh, look at that. We're making less than $2 more, even though they're paying us interest more times per year. In the first bank, they're paying us interest 4 times a year. Here, 12 times per year, and it was less than $2 difference between the two banks. Okay, well, weekly, surely that's got to be more because it's got a whole lot more interest being paid each time. So let's put our $1,000 in. 1 plus 0.04, let me put that in the parenthesis, 0.04 divided by 52 this time, and raise it up to 52 times 10. Okay, that's your dividing by n and multiplying by n. Okay, let's see how much money you're getting paid every single week. They're giving us interest every single week. Look at that. We have $1,491, and we'll go with 60 cents. So not even $1 more, and we got paid interest a whole lot more times. Why do you think that is? Because it feels like if we're multiplying by 52 up here, that's certainly more than multiplying by 12. Why are we not making big differences here? Because even though we're multiplying up here in our exponent, we're still dividing by that same number here, and we keep dividing by bigger and bigger numbers. We're dividing the 0.04 by bigger and bigger numbers, so it's kind of reducing that increase, and that's why that's happening. So now let's see what happens for 365 days. It should be more money, so we'll take a look. So instead of 52, we have 365, and then it will be, 365 times 10. All right, let's see what we get. Look at that. $1,491.79. We got 19 more cents, and they paid us interest every single day. It's because the amounts aren't changing as much when they're paying the interest, and so it doesn't make as big a difference. So there's not a big difference between any of these banks. You would then get to make a decision which one's closest to drive to or something like that, which one's most convenient for you. That might be the best choice for which bank you would choose to put your money in at this point. All right, I hope that was helpful. Let me know if you have any questions, and I'll see you in class.